These are typical plots of the ignition delay times, logarithmic scale, versus 1000 over T for a hydrocarbon. In the very high and the very low temperature regions, the normal behavior is observed, namely the decrease of ignition time with the increase of temperature. However, in the region between, the negative temperature coefficient region, NTC, the opposite behavior is observed. Below around 1000 degrees Kelvin, the ignition times become slower with increasing temperature. Note that the ignition delay versus 1000 over T, as one moves from left to right, the temperature is decreasing. In other studies, looking at the initial consumption of fuel shows that there is an inhibition process going on at intermediate temperatures, meaning the NTC region. This implies that at these temperatures, there is a reaction which inhibits the consumption of fuel, which in turn slows down the time it takes to get to ignition. This slide, shown previously, shows that there is a significantly different species selectivity at low temperatures as opposed to high temperatures. At low temperatures, oxygenated species such as ketones, aldehydes, peroxides, and cyclic ethers are predominant. This shows that the species resulting from the addition of oxygen are very important in low temperature chemistry. It is the peroxides formed from the addition of O2 to alkyl radicals which play a significant role in the NTC behavior. There is a unique behavior in the low temperature region of combustion that is distinctly different from high temperature behavior. One is the increased amount of oxygenated species, and the other is the NTC behavior. The key to this behavior is the main path of low temperature chemistry. Under low temperature, there is another path that dominates the autocatalytic character. The main path of low temperature oxidation is the addition of two oxygens to an initial alkyl radical, which, at the end of the path, produces two hydroxyl radicals. The initiation is the abstraction of hydrogen and the formation of the radical. The second step is when oxygen is added to this radical to form a peroxyl radical, shown generically as RO2. The third critical step is the intramolecular abstraction of the peroxyl to form a hydroperoxyl and a radical at another carbon, and this is represented as QOOH. The fourth step is in another addition of a second oxygen to form the peroxo-hydroperoxyl alkyl radical, commonly known as OOQOOH. This peroxyl-hydroperoxyl alkyl radical is the precursor to the production of two hydroxyl radicals. Thus, in effect, one radical is lost in the abstracting of the first hydrogen from the fuel alkane, but two OH radicals form, producing the autocatalytic effect. This slide shows the dominant reaction in the low temperature path of an N-heptane from a structural point of view. After an oxygen molecule is added to the alkyl radical, we have an ROOH radical produced. Thus, on the hydrocarbon, there is a highly reactive group, the radical on the oxygen. This highly reactive group can either react with other molecules, or actually within the hydrocarbon itself in an intramolecular reaction. In fact, the intramolecular reaction is more likely because, since the reactive group is attached, it is always very close, increasing the chances of a collision. Remember also that a six-membered ring of the tetrahedral atoms involves no ring strain. So, through the twisting around of the six atoms with a reactive group at the end, the oxygen radical and the hydrogen can come close enough to react. This makes this particular product more favorable. From the OOQOOH species of the low temperature pathway, two hydroxyl radicals can be produced, thus promoting the catalytic activity of the low temperature hydrocarbon reactions. This slide shows the changes in the electronic structure that eventually give the two hydroxyl radicals. In the first step, the COOH group produces one OH, while the COO group simultaneously extracts a hydrogen from the carbon. The original carbon then forms an aldehyde, and the abstracting CO becomes a COOH group. In the second step, one again an OH is produced from the COOH group, and simultaneously a carbon-carbon bond is broken to produce again another aldehyde. The key step in the production of each of the hydroxyl radicals, OH, is the decomposition of ROOH to RO plus OH. The oxygen-oxygen bond of the hydroperoxyl group splits into two radicals, one of which is an OH. Of course, the main path is not the whole story. There are many side paths producing other oxygenating species, particularly more aldehydes and cycloethers, a ring species where one of the atoms is a carbon. But where does the NTC behavior come from? Remember, in looking at the ignition delay time, with increasing temperature, there is a time when the ignition delay actually becomes longer. Expected behavior is that the ignition delay should actually decrease. At lower temperatures, below 1000 Kelvin, the main low temperature path predominates. In an intermediate area, when the high temperature path is not dominant and the low temperature path should prevail, there is an inhibition in the ignition behavior. Studies have shown that this intermediate region, there is a shift in equilibrium of the oxygen addition reaction. In effect, the oxygen shifts away from the products, thus inhibiting ignition behavior. This occurs in the NTC region. This stops the main flow of the low temperature pathway, making longer ignition delay times.